Remote. Mute. Bakara nga mugenda mu moto. Ate nti oli asotinga obutumba.
What
Good evening, everyone. I was still waiting for the number at least to clock 20, but it seems some people might not be able to show up. We shall not wait for them. We should need to go on because, for example, even me, I've just been driving from the village very fast to come and meet this lesson. By 8, I was exactly home. So if for them, they are not showing up, for us, let us proceed. So last time we had introduced work done and energy. And we had briefly talked about the definition of work done and energy as a whole. And we defined some of the principles and definitions of energy. Now, for the work done, a reminder or a recon on how work done is handled. If you have a body, and that body is acted upon by a force F at an angle theta, and this body is going to be moved a distance of x. Then when you resolve the component of the force, vertically you'll have F sine of theta. Then horizontally you'll have F cos of theta. So it is this force that drives that body. So I can call that the driving force. So that force D is the force we need to use to find the work done. So the work done would be D times small x, which D is actually F cos of theta times x. Now, it means all the work done formula we have ever heard of in the world comes from x F cos of theta. Or work done is equal to FD cos of theta. Sometimes small d is equal to the distance they're talking about. Now, the other aspects you know of work done being just force times distance, this is where they come from. They come from the concept which says that in that situation, the angle is what? The angle is 0. So if theta is 0, then cos of theta also will be 1. So in that case, the force will act horizontally on the body. So if the force acts horizontally, that is why work done is equal to force times distance, or work done is equal to FD. But besides that, work done originates from an angle of an inclination for the force at all times. So with that reminder, we can talk about a new definition today, which is going to be work done against gravity and work done against frictional force. So work done against gravity and friction. We all know gravity. And then we also know what we call friction. So we can do work against friction, we can do work against gravity. We know gravitational pull is that force we have or we experience, which brings us back down to the surface of the earth. Okay? In that regard, it means that if you can take into consideration the work you have done in bringing down a body, then you're doing work, or taking it up, then you're doing work against gravity. If you do work against frictional force or to overcome friction, then you're doing work against friction. Okay? So in that regard, if you have, for example, case 1, if you have a body which is just on the surface and there is small f frictional force, then there is a driving force, capital D. The body has its normal reaction. It has got its weight mg. It has its driving force, capital F. When they ask you to find work done against gravity, it will be equal to the opposing force, which is friction, times the distance this body is going to move as it is overcoming friction. So friction times x. But friction is equal to mu r, where mu is the coefficient of friction. Mu is what we call the coefficient of friction. Then R is what we call the normal reaction. So this R is always equal to, because R is in the line of the upward force and the line of the downward force, then because the body is not moving off the ground, in that case always R is equal to mg when the body is on a horizontal surface. So therefore, work done against friction will be the frictional force times the distance covered, which frictional force is mu r times the distance. And we have seen that mu r is mg times x. So this is always work done against friction on a horizontal surface. Then work done to move the body. Work done to move the body. is equal to work done by the resultant force. You know the resultant force is got from mass times acceleration. So the resultant force is actually capital F minus small f. So if capital F is the driving force, it will overcome friction, which is mu r. So MA will give us the driving force minus mu mg. Now, if I want to find work done to move the body, work done to move the body will be the resultant force times the distance the body has moved. And the resultant force we have got is capital D minus mu mg times small x. So that is MA times x, which is work done by the resultant force. Then the other case. So this is Roman 2, this is Roman 1, this is Roman 3. We have work done against gravity. Work done against gravity. If you consider a body which comes from the ground, and this body has been raised to a certain height, vertically, then that height covered can be small h. And the body is of mass m. Remember, this body has a weight mg. So this weight mg is the force you are overcoming. So the work done against gravity will be equal to the work you're doing, which is doing work on the force F, on the force which is the weight, times the distance you're going to cover. But the distance we are covering in this case is the vertical height. So work done against gravity would be mg h. So this is our work done against what? Gravity, when a body is being raised vertically upwards. So when a body has been raised vertically what? Upwards. So that's why we conclude and say work done against gravity is a measure of gravitational potential energy. Is a measure of gravitational potential energy. Okay. Able to understand? That is a measure of gravitational potential energy. I think I'm green. Then we will take 65. Blah, blah. So whenever you're looking at work done against gravity, it's the same as getting. It's the same as getting work done against the gravitational potential. You are same as the work done as a measure of the gravitational potential energy. So when you measure gravitational potential energy, you are getting work done to move a body vertically upwards. Now, these ones are a little bit obvious. When you have a horizontal body, on a horizontal surface, when you have a body on a raised platform, but what if the body is being raised along an incline? That is where the most interesting bit comes in. So can you first put down these definitions? Or if you have a question, please let me know so that I can handle it before I go to the last definition. And then we'll go for examples. So when you're ready, let me know so that I can take you through the next definition, which is going to be when a body is on an inclined plane. You can contact people on the group. Some people I think are not aware that the lesson began even, because people are just coming in now. Okay, any questions on these definitions? Are we there, guys? The silence is too much. I want us to have the last. Okay. Fatima, you raised the hand. Yes, please.
Teacher, me, I've just come.
Fatima. I'll send you the video. You'll inbox me on WhatsApp. Okay?
Okay. Yeah.
Hope you have my number. Then the other guy who I'm supposed to send the video, I'm going to send it right after this lesson. You remind me. Or was it permutation? Okay. The next definition now I'm bringing on board is when a body is moving on an incline. The work done by a truck, the work done by you climbing a hill, the work done by you running a hill. How is that work taken into consideration? That work done is in this format. Case 2, on an inclined plane. I have a body that was initially down here, and then this body moves the distance upwards and reaches that position. This was position A, reaches position B. And this body has covered a distance X. Of course, if this body is on an inclined plane, it experiences 1, a normal reaction. 2, it has its weight, mg. 3, it has a component of mg sine theta. Then 4, it has another component here of mg cos theta. Those of us who never saw these definitions, we can always cram them. But if you did not attend such classes, let me know. That's why I want to arrange a video for mechanics so that we can have some of those first lessons reviewed, so that I can take you through some of these aspects I'm talking about. Then, if the body is moving upwards, there is friction experienced. Yeah? Now, when this body has risen up to that height, it will have risen to what height vertically? It will have risen to a height which is small h vertically. But because of this angle, consider a right angle triangle so that you can find h. If this is theta and this is x, then h is equal to x sine of theta. From Pythagoras Theorem, if this is a right angled what? Triangle. Now, first and foremost, when the particle is at position B now, the work it's going to do, it would have been, initially here we give it a velocity, initial velocity. Maybe it reaches here and it stops. The initial velocity here is u, then the final velocity here v is 0. So it means it has lost, remember energy conservation, kinetic energy it had before has been lost. But that kinetic energy which has been lost, it's going to be lost to potential energy, which we have gained, plus the work we have done against friction. So other people can make this other definition. And they say, the work we have done against friction is equal to the loss in energy, or is equal to the change in energy. What does 75 mean? Others can say work done against friction is equal to loss in energy. Also, this definition can help you interpret such problems. Others can say work done against friction is equal to the loss in kinetic energy, loss in energy, which is kinetic energy we have lost, we had earlier, minus the potential energy we have gained. The answer you get is the work you've done against friction. So any of these three are okay. But in most cases, we shall use this one. So if we are to use that one, what does it mean? It means, first and foremost, friction is equal to mu r. Now, if the body is in this form on an inclined plane, always r is equal to mg cos theta. Because you consider the force which is in line with r, since the body is not getting off the inclined plane, then as it is in this form, the r you experience here is equal to this other force it is in line with, which is mg cos theta. So with that regard, the friction would be mu mg cos theta. So the work you would do against friction would be mu r times the distance along which the friction is being overcome. We are overcoming this friction along the distance x. That's why I'm multiplying by x. So finally, the expression would be mu m g x cos theta. So if that is the expression for work done against friction, then the expression for work done against gravity. Remember, we saw that work done against gravity is the measure of gravitational potential energy, which is always mgh. Now, according to the height here, the height is not just the usual h. The height is x sine theta. So this consideration has to be made for x being equal, for h being equal to x sine of theta. So work done against gravity will be mgh, which we have said is mg now times x sine of what? Of theta. Then finally, the kinetic energy we have lost would be got from our half mu squared. The initial inner kinetic energy was a half mu squared. So among the questions which come in these numbers, they can ask you for the distance. How far up does the body go before it stops? So you can use energy conservation. But before, we are using equations of motion. Now, when I simplify these equations, you're going to see that they deduce the equations of motion. That's how some of them could be derived. Now, kinetic energy loss, if I use the first one, I'll have R half mu squared is equal to potential energy gain, which is mgh, plus work done against friction, which is mu r times x. When I substitute the necessary items, I'll have R half mu squared is equal to mg x sine of theta plus mu mg x cos of theta. And it is from here that you can get to learn that the weight of the body does not matter when the body is climbing up a hill.
Teacher.
It depends on the velocity it had in the beginning,
Teacher.
and the acceleration due to gravity, as I'm going to show you. When you divide
Teacher.
everything by m, can we lose m? When you lose m, yes?
Excuse me, teacher.
Yes, please.
If I'm sorry, but if you can please back up on work done by against gravity.
Okay.
I lost track.
Okay. It's okay. I was saying work done against gravity is the measure of gravitational potential energy, as I discussed earlier here, whereby it's got from when a body is going up, you are overcoming its weight. And you're overcoming it through a distance, what? H. So the force you're dealing with is mg. So the work you do against gravity shall be the force times the height you've covered doing that work against that force. Now, because the force is mg, I will multiply by h, and I'll realize work done against gravity is equal to mgh. Now, according to this other one, on an incline, the h is always the vertical height. Vertical height means an upright height, not this inclined x distance, but vertically from here up to down here. If I draw a vertical line straight perpendicular to the ground, then that is the vertical height. So this vertical height, I can get it from Pythagoras Theorem, which is actually h is equal to x sine of theta. Why sine? Because if this is the right angle triangle, and this is theta, and this is x, and this is h, then sine theta is h over x. When you cross multiply, you can get h as x sine theta. That's how I came up with this one. Are you better now? My friend, are you fine?
Yes. Thank you very much.
So when I divide here by m, I'll remain with u squared is equal to 2gx sine of theta plus 2 mu gx cos of theta. So u squared would give us 2gx into sine theta plus mu cos of theta. If the body did not stop and attained some velocity, then we would have attained the new kinetic energy. So you would have added it here, that plus kinetic energy what? Gained. So the loss in the total energy you had before would be the potential you gain plus the work you do against friction plus the kinetic energy you have achieved at that point. But now, because it has stopped, the kinetic energy at that point was 0. Now, this is the expression which when made the subject, you can now get the distance covered as u squared over 2g into sine theta plus mu cos of theta. Of course, when they are in this form of equations, learners get a little bit bored. But when we come to problems, you'll see how interesting they are and how easily we can handle the question. Okay, so basically that is the concept. So what I wanted you to pick out of this is this idea. Even if you did not simplify further, but as long as you pick this idea right, you can always handle these challenges. Unless if someone has a question, if no question, you can download. And the principle we are using still, one would say, where there's some other people, instead of losing this, they would say mechanical energy conservation. Mechanical energy at A is equal to mechanical energy at B. But the mechanical energy at B cannot be equal to the half mu squared we had before to give us mgh. No, why? Because we have lost some energy plus energy lost. And the energy we have lost is the work we have done against what? Friction. Fatima, your hand was up.
It's okay. I saw what I wanted.
Okay then, thank you. So with those definitions, we need examples now. So download them as I write down the example. Hanani Wasike, your hand is up.
Teacher, Rahim is lost in the last part. He was trying to solve for me, but it's hard for me to explain to him while writing. Please explain to him.
Which part? Which part?
Teacher, you asked.
Please, people, don't fear. Ask questions. Who is asking? Faraj. Faraj, please come out and suppose your question. When you're sitting in the paper, you'll be alone. So come out, please. Don't be shy. We are scientists. We don't shy. Yeah, Yeah.
Teacher, I was still asking the same thing. The same thing this guy had asked earlier. I had not yet seen it.
But now you've seen it, eh?
Yeah. Let's first do an example. I'll tell you after.
Okay. Now, okay, final. Are you done with your write-up? First, write down the question, because I don't want network to interfere when you don't have it. So this one is a tricky question. It is not a forward motion, an upward motion. It's a downward motion. I had forgotten to comment about it, but we shall follow. This time round, the body is starting from up, sliding down. So when it is already up here at A, it's possessing potential what? Energy. When a body is released, the initial velocity is 0. It travels, a slope is of 10 meters, a block of mass 50 is released from the top of the slope and travels down the slope, reaching the bottom with a speed of 8. So it reaches down here with a speed of what? 8 meters per second. But as it is going down, we are doing work against friction. And the work we are doing it through 10 meters. So the potential energy we are going to lose is equal to the kinetic energy we are going to gain at the bottom, plus the work we are going to do against what? Friction. I don't know that people are following this carefully. Now look at the question. The definition I discussed was for going up, losing kinetic to gain potential. Now this question has come when you're losing potential, gaining kinetic. You just need to interpret the concept and have the mechanism of energy conservation. And the principle of conservation of energy states that, of mechanical energy states that total mechanical energy should be a constant. So the energy you had before should be the same energy you have down. If it's not the same, then you've lost some of the energy as a result of doing work against friction. Now, there is an angle here, theta, but they say tan inverse of theta, okay, of 3/4 is the angle theta. So you design a right angle triangle. Tan is 3, 4, this will be 5, and then this will be theta. So that sine of theta can be achieved as 3/5. Then cos of theta can also be attained as 4/5. Now with that concept, I can now substitute RF, not RF, mgh will be equal to RF mv squared attained plus the work we have done against friction, which is frictional force times the distance going down. Now, according to this question, never wanted you to take this definition straight away. The question first wanted you to find the work you've done against friction. So the work we have done against friction, remember I told you, it is the frictional force times the distance the friction is going to cover as we do work against it. Okay? And that distance in this case is 10. So we need to find the frictional force first. But they never gave us the coefficient of friction. Oh, okay, we can use that same formula for energy. Check this out. Make friction the subject. Do you see that mgh minus rf mv squared is equal to friction times the distance x covered. And with this regard, friction F is mgh minus Rf mv squared divided by x. That is why they wanted us to find, or they said work done against friction. Then work done against friction is this one. But if they had asked for friction, you would have used that. So work done against friction would be, the mass is 50 times 9.81 times the height.
Excuse me, teacher.
Yes, please.
Teacher, do you mind going a little back behind me?
This side? Yes, please.
Yes, teacher.
I go back where? I repeat the whole thing, or I go back some point?
No, actually, where you began the calculation from.
Did you get the interpretation on the slope?
Yes, teacher.
Okay. Did you get this expression, this word statement?
Yes. Yes.
Because we are at that instant, we are losing potential. And as we lose potential, we are gaining kinetic energy. And we are losing energy.
Kinetic.
Okay. Now, because they gave us this statement in the question, that the angle of inclination is tan inverse of 3/4. I'm saying the angle of inclination is theta. So tan inverse of 3/4 is theta. It means tan theta is 3/4. When I extract that out using a right angle triangle, I will have 3 on the opposite over the adjacent. So the hypotenuse becomes 5, because 3 squared plus 4 squared under the root will give us 5. So I can deduce sine theta, I can deduce cos theta. Is that okay?
Yes, teacher.
Then this equation, was it fine?
That's actually where I wanted.
Okay. The potential energy we had here, this is the potential energy we have lost. The potential energy we have lost is this one. Okay? The kinetic energy we have gained is this one. The work we have done against friction is this one.
Okay, thank you, teacher. Yeah.
So, can we substitute for the height? The height h, I showed you how we get the height. Height is supposed to be x sine of theta. So it will be 10 sine of theta, which is 10 times 3/5. By 5 once, by 5 2. The answer is 6. So height is 6 minus 1/2 times 50 times 8 squared. 1/2, this is 25. So this will give me 300 times 9.81 minus 25 times 64. 25 times 64 is the same as 32 times 50, which would have been 150 plus 10 plus 100, which is 250, which is 2,500. 25 times 64, is it 2,500? No. 25 times this one. 25,000.
25 times 64 is 1,000.
It is what? It can't be 1,000. What do you get?
Yeah, it's 1,000.
This was 1,000.
1,600.
1,000.
600.
Okay. Then 3 times 981. That is 2,700 plus 243, which is 293.
Two 943.
43. Yes. What do you get?
1343.
Joules of energy. What's wrong with my pen? So this is the work we have done against friction. Okay. Then the second question, magnitude of the frictional force. You see, I showed you the formula for finding frictional force. So frictional force is equal to the work done against friction divided by the distance friction has covered, which is 134.3 divided by 10. And the answer is 134.3 joules. Then they are saying coefficient of friction. Titus, your hand is up. Go ahead.
Teacher, I'm not quite getting this, how you have answered this question.
Yeah?
I'm not quite getting how you have answered this question.
But have you got to interpret that the question is a downward slope?
Yes, teacher. Very well.
Yeah. So we are using the concept of energy we have lost as we are up, and then the energy we have gained on sloping down. Look at this board. Let me get a marker here. You see this marker is on this board. It is resting initially. If it is resting, when I release it, it goes down.
So we are not seeing the board.
Yeah, you're not seeing the board. How about here? Can you see it?
Yes.
Yeah? You see the sloping down? When I release the marker, it goes down. Here initially it doesn't have a velocity. But when I release it, it starts losing because there is a height it has. For example, if this is where it is starting from, there is a height from here up to down, which is a vertical height. So when it starts climbing down, sliding downwards, the height goes on reducing, meaning it is losing potential because potential is mgh. So if the height goes on reducing, the potential is reducing. So in actual sense, we are losing what? Potential. Okay? So when you lose potential, what are we gaining? It was at zero velocity. The velocity goes on increasing. So it reaches down here, the velocity would have increased. So would have gained kinetic energy from a half mv squared. Okay? So with that regard, we have lost potential energy and we have gained kinetic energy. But when you compute, the kinetic we have gained here is the total energy down. It's not the same as the total energy we had up here. What does that mean? It means we have lost some of the energy along the way. And how have we lost it? We have lost it by doing work against frictional force. So that is why the energy you had before, which was potential, when you reach down here, that energy should be the kinetic you've gained plus the work you've lost, or plus the energy you've lost as a result of doing work against frictional force. So that's how the equation statement came about. Then the rest are the formulae we discussed earlier that we employ and we use and find whatever we want to find. I want to get an example which is having motion upwards.
Yeah, that explains how we have gotten the formula of mgh minus a half mv squared is
equal to work done against friction. Yes.
Yes.
Have you got that one right?
Yes. Then this next step of where we make force the subject.
Yeah, okay. Now, do you see this equation here? Have you seen that?
Yes.
That is the equation for work done against what? Friction. Not so. Yet work done against friction is friction times the distance the friction has moved. When I divide both sides by x, or this way by x, I get frictional what? Force. That's why I did this. Does that make any sense?
It does.
Okay. So can I finish the last one? Friction is mu r. They want us to find coefficient of friction. So therefore, coefficient of friction mu will be the frictional force divided by r, which is the normal reaction. So it will be 134.3 divided by the normal reaction, which is mg cos theta. This will give us 134.3 divided by m is 50 times 9. This is math, 9.8. Sorry, I used 9.81. Okay, times the cos, which was what? 4/5. So you can compute and give us the value of mu. Mu, remember, lies between 0 and 1. If you get mu, which is a negative, stop working. Pray to God again, then you restart the number, or first go for another number. If you get mu greater than 1, impossible. When mu is beyond those two values, whatever motion you're having is impossible. It means if mu is that very big, the particle can never move. And yet for us, for you, as it is moving.
0.34.
0.34. 4 decimal places.
2, 6.
Mu has no units, eh? So you can have that down. Unless someone has a question. Okay, there is another question. So have it written down very fast so that we can go through it. We shall stop at that one. Are we there?
Yeah.
Okay. Same now, this question is a little bit different because of the motion, the direction it's taking. This time around, we are coming from down and we are projecting the body at initial velocity, which is 5.6 meters per second. This body is going to go up the incline until it reaches position B. They have said that theta is equal to tan inverse of 4 over 3. The other one was tan inverse of 3 over 4. The coefficient of friction in mu is known, it is 4 over 7. So therefore, as the body is going to climb up, they want us to find the distance x, because x is AB. Remember the height here, it's going to cover a height small h, which is equal to x sine of theta. But also recall this, when I consider this as a right angle triangle, then you can extract it from there and get to know what x is all about. So when you are down here, we are going to lose. Some other people want to interpret it in this form, that mechanical energy at A should be equal to mechanical energy at B. But mechanical energy at A is just fully what? Kinetic, which is equal to the mechanical energy at B, which would have been mgh. But they are not the same. Reason we have lost some energy as a result of doing work against frictional force. So plus work we have done against friction. So with that regard, can we now interpret this? There's my gentleman who had not interpreted that very well in the last number. I don't know whether he's fine now. My friend who had a problem with that in the first number, are you now feeling better? Okay. Now, because we are looking for the distance x, we have seen what h is all about. Then also work done against friction. Remember, is frictional force. Frictional force times the distance frictional covers, which is mu mg x cos of theta. Then we can now substitute and have our f mu squared is equal to mg x sine of theta plus mu mg x cos of theta. Then my equation I derived earlier can be of help. We are looking for x, so x will be equal to r half u squared over g sine theta plus mu g cos theta. Then you substitute, which is a half times 5.6 squared over 9.8 into sine theta is, according to our triangle, if you extract out a triangle depending on the statement for the angle, theta is 4/3. This will be 5. So sine of theta is 4/5 plus mu, which is 4/7 times cos, which is 3/5. Can someone compute with a calculator to get us the value of x? Others can work using a longer method by splitting it. Yeah. Others can use, I'm going to show you using equations of motion that we can get the same answer. Compute that with a calc. What answer do we get?
1.9. 9162
meters. Method 2. Final velocity is 0. Initial velocity is 5.6. The height we are covering, or the distance we are covering, is going to be h, which is equal to x sine of theta. So v squared is equal to u squared minus 2g or minus 2a s. Now, if you consider this acceleration, let me consider this acceleration. If I consider this acceleration, then acceleration is going to be what? When the body is going up, Yeah, the driving force is 0. But we are going to overcome. We are going to overcome what? 0 will overcome mg sine theta, overcome frictional force to give us the resultant force. So the resultant force would be MA is equal to a negative, yeah? It's going to be equal to a negative mg sine theta a plus mg mu cos of theta. When I divide everything by m, I get A as equal to a negative g sine of theta plus mu g cos of theta. So when I get this A, I have to substitute it here. So I would get because the final velocity was 0, there's one interpretation I've not made. When the body is coming to final velocity 0, it is decelerating, so acceleration is a negative. So A finally becomes a positivity. So if A is a positivity, when here V squared is equal to 0, you'll have 0 is equal to U squared minus 2AS. So U squared will be equal to 2AS, giving us 2 over G times S, which S is the X, the distance up the incline, times sine theta plus mu cos of theta. You will find that this equation is the same as this one. Then you substitute, you get the same answer. You are looking for X, so you make X the subject, which is U squared over 2G into 4 over 5 plus 4 over 7 times 3 over 5. Then you substitute 5 you had 5.6 squared, 9.8. The answer is the same. So if someone is not comfortable with energy, you go back to equations of motion. But you should know how to find resultant force because it is the acceleration you have to use. And then you should know that this body was climbing up without anything pulling it, but it overcame friction and overcame mg sine theta. But if the question specifies and says using energy conservation, then no shortcut, energy principles. So you can have that question down. Then I send you some numbers here to enjoy. Don't worry, I'm sending from understanding. Maybe tomorrow I will introduce the other. When are we meeting again? Friday. I will introduce. I'll do some numbers from Humphrey. Maybe 1 or 2. Then if I can do some other energy numbers in vertical sense, then we shall introduce power. Okay, any questions? Those of us with understanding mechanics, whether soft copy or the number of pages I've sent, we are on page 261. That's where you can find the numbers. You have some around what? 16 numbers to do that. Please, you do all the numbers. That's why I call the group solve all. It means you solve all the numbers as they are. You don't solve them, you'll be in trouble. And if you're a physicist, you'll enjoy the mechanics of physics because these concepts are the same. You just have some more wording of physics that you get, but the calculations are the same. Okay. Can call it a night. I haven't rested at all yet, so I'm still waiting for you guys to finish. So I'm closing on your notification that you're done.
You get work from. For me, I've looked for it on the WhatsApp group. I'm not. Please. Send it on his WhatsApp group, right? Look. Yeah? Exercises.
Human, I'm teaching my students. Let me see if I can view you here. Hey, they are not seeing you. That's your new teacher for the evening. Say hello. Hmm? You see the students are waiting for you. Speak some math. Speak mechanics. Hmm? Speed. Now, how did you get into my seat? Hmm. Let me give him understanding to start handling. Those people don't know how you handle. Yes. Baje ku mama wangu. Eh?
Teacher,
Yes.
is that phone on your WhatsApp group?
What? Is there what?
Is that you send
I can't pick your words. What's happening to your phone? Your network is poor.
I think she's not in the WhatsApp group.
Ah, send me a message. What's her name? my phone. This person. Please, whoever is not on the group, inbox me so I can add you, and also see how I can bless other people. The work is on WhatsApp, yes, because I've taken screenshots of the book. What is it? Okay, this man, I'm in his space. So let me close. We can meet next time. For more questions, get me on WhatsApp. Ryan, you want to enjoy your mechanics? Bye-bye.